Hello, my name is Garrott, and I am here to share the data from the abstract titled Intra-Lesion Temperature Rise and Local Impedance Drop are predictive of lesion growth on an RF ablation catheter with many electrodes. This work was sponsored by Boston Scientific, and all authors were employees of Boston Scientific during the time of data collection. The overall objective of this benchtop study was to evaluate the relationship between a local impedance metric and the intramural tissue heating during RF ablation. This was done by using thermocouples embedded within ventricular tissue. It's well known that for cardiac RF lesions, a tissue temperature of 50 degrees Celsius is necessary for adequate lesion formation. In the absence of a metric that actually measures underneath the surface of the tissue, we hypothesized that a local impedance measure could be sensitive to volumetric tissue heating and provide feedback on lesion formation. In order to measure intralesion temperature, 3 thermocouples were placed in line at depths on the surface at 0 millimeters, 2 millimeters under the surface, and 4 millimeters under the surface. These thermocouples were placed into the tissue 0.5 to 1 millimeters lateral to the catheter tip. Local impedance was measured by a method previously published as DIRECTSENSE on Intelinab MyPhi-OY. Lesions were created on fresh ventricular swine tissue that was preserved in cardioplegic solution and explanted day of experimentation. A total of 62 lesions were created in a bath designed to mimic the blood pool temperature, conductivity, and flow. Catheter irrigation was standard at 17 mils a minute for powers less than 30 watts and 30 mils a minute at powers greater than 30 watts. RF was applied at powers ranging from 20 watts up to 50 watts to span an entire working range of low power up to high power. And RF was applied until a local impedance drop of 10, 20, 30, or 35 ohms was achieved. Lesions were stained with TTC, imaged, and measured. Now let's start to walk through the results. Let's first start with the column on the left-hand side. Here you'll see 3 scatter plots looking at the relationship of local impedance drop, mean temperature rise, and surface temperature rise to lesion depth. We know that lesion formation follows a mono-exponential growth curve. So as you look at the local impedance drop plot, you can see that with increases of local impedance, you see increases in depth and that there's a strong correlation. You see a similar trend with the mean temperature rise. However, when we look at surface temperature, we see that there's not as strong of a correlation and there's quite a bit of spread of the data. This could be because surface temperature is sensitive to other variables such as cardiac flow or catheter irrigation and doesn't offer quite as strong of a correlation to lesion depth. Now let's look at the representative traces in the top row. Let's first talk about the temperature. So you can see in the light blue we have surface temperature, 2 millimeter temperature in dark blue, and 4 millimeter temperature in royal blue. The average of those 3 traces is given in the green. You can see that as RF is applied, there's an increase in temperature throughout the entire portion of the application. You see this strongly in the temperature probes underneath the surface, and while there is a temperature rise in the surface temperature probe, it's not nearly as great as the others. You also see that the local impedance drop strongly follows the mean temperature rise and the temperature rise from the 2 millimeter and 4 millimeter probes. This relationship holds true at both low power, 20 watts, and high power, 50 watts. We wanted to quantify this rate of change, so we looked at the time it took for both the local impedance drop or the temperature rise to reach 63% of the maximum. And what we see is that overall there's a very strong correlation with the rate of change between local impedance and temperature. Finally, let's move to the figures in the bottom row. In the first figure, you can see that there's a strong correlation between the local impedance drop and mean temperature rise. This is telling us that there's a strong relationship with local impedance and the volumetric tissue heating. We know that conductivity and heating are directly related, and as local impedance is a measure of the changes in conductivity, that's why we see such a strong relationship with the intralesion temperature. Additionally, as you look at the box plot, you can see that for increasing local impedance drops, you have increases in the maximum temperature. Notably, for local impedance drops greater than 10 ohms, you start to reach that threshold of adequate tissue heating of 50 degrees Celsius. Also, at impedance drops greater than 35 ohms, you're starting to reach the upper threshold of tissue heating of 100 degrees Celsius. So overall, what we found in this study with explanted swine cardiac tissue was that both local impedance drop and mean tissue temperature strongly correlated with lesion depth, while surface temperature was not as strong of a predictor. The local impedance drop informed volumetric tissue heating with a tight relationship to intralesion temperature across the entire working range of both lower powers and higher powers. So overall, we found that local impedance is a valuable indicator of intralesion temperature and lesion dimensions. Thank you for your time.